Hello, this is Math 2231 coming to you from the College of DuPage during the summer of 2020, and this lecture is a first continuation of the lecture entitled Computing Indefinite Integrals and Solving Initial Value Problem. When last I left you, you were solving these 6 problems. I hope you did it, but if you didn't, here's another chance. You know what to do. Let's see how you did. Well, here you have the sum of 3 terms. We're going to do this term by term, and we're going to jerk the constants out every time. So the 5 just sits there, but then we're integrating t cubed, and so that is going to be 1/4 t to the 4th. The minus 10 just sits there, and we're integrating t to the minus 6. So that is going to be, when you add 1 to the exponent, you're going to minus 5, so it is 1 over minus 5, and that is t to the minus 5. And then when you integrate 4, you'll get 4t. And then we actually get constants every time we take the integral, but we can lump them all together here and just have one big old c at the end. And then we should simplify this because I'm going to ask you to plug in numbers. And so you want to simplify it, and if we simplify doing the arithmetic, this is what we get. This problem, again, we're going to do it term by term. We add 1 to minus 8, and we'll get minus 7, and we'll divide by the minus 7. So this is going to be 1 over 9, x to the 9 minus 1 over 7, x to the minus 7, plus c. We lumped all those constants together into one big old constant. Here a little bit more involved. We jerk the 3 out, the 7 out, and the 1/6 out. But then we have x to the 3 over 4, x to the minus 5, and x to the minus 1/2. So when we add 1 to the exponent, divide by the new exponent, we get to do some fractions. When we add 1 to 3 over 4, you get 7 over 4. When we add 1 to minus 5, you get minus 4. And when we add 1 to minus 1/2, we get plus 1/2. And we divide by the new exponent in each time. And we lump all our constants together, and we simplify, and we get this expression. Again, fractional exponents are good when doing calculus calculations of this kind. This problem is pretty straightforward. All we're doing is the integral of dy is equal to the integral of 1 dy. That's going to be y plus c. Now here, it's important you realize there is no product rule, so what we have to do is multiply this out using algebra. So first we do algebra, then we do the calculus. And again, you see this is between the integral sign and the differential sign, so that means this stuff is sort of inside parentheses. So what we're going to do is we multiply this together, we FOIL it, and we get these 4 terms. Notice that when we took w squared times w to the 1/3, we get w to the 7 over 3. And now we're going to do this term by term. We'll factor out the constants, and we will get 2w squared minus 1/4 w to the 4th plus 3w to the 4 over 3 minus 3 over 10 w to the 10 over 3, and we lump all those constants together. Make sure that you can follow all of these calculations because one day soon you'll be doing these yourself. Here again, we're going to do, there is no quotient rule for integrals, and so what happens is, what we're going to do is we're going to divide this x cubed into each one of those terms using the distributive property. So here we'll have a net of 4x to the 7th, here we'll have a net of 2x, and here we'll have a net of 15 over x dx. We're going to do this term by term. We're going to lump all our constants together. And so the 4 and 2, minus 2 and 15 just will sit there. We pull them out of the integral, but then we integrate here and divide by the new exponent. We will get 1/2 x to the 8th minus x squared plus, this is going to be 15, and this is the natural logarithm of the absolute value of x. And again, we lumped all our constants together. Now here's a batch of additional problems for you to do. Again, I want you to evaluate each of these indefinite integrals. Looks like we have 5 of them, and you know what to do. And I'm also asking you to check your answers by using the derivative of the right hand side, which should end up being the integrand. We'll see how you do in 31.2.